In this video, I will show how to use the properties of a quadratic function to solve an applied math problem. So let's read the problem. A demand equation is given. So what is a demand equation? It's equation that relates the price and the quantity sold. So in this case, price is the output variable, x, the quantity is the input variable. The relation is always decreasing because the higher the price, the smaller quantities are demanded, and the lower the price, the higher quantities are demanded. And this equation is given to us by this formula. So we have negative 1/10 x plus 150, meaning if we know how many quantities we want to sell, we can figure out the price at which to sell them. So let's answer a question in part A. So what is the revenue if 100 units are sold? Well, first here we have to recall that revenue is the total amount generated from the sale. So if we're selling 100 units, that means to find the revenue, we have to multiply 100 units that we sold by the price of each unit that we sold, which we can find using the demand equation. So the price of 100 units is simply P of 100 using the function notation. And now we can easily evaluate it. So P of 100 is negative 110 times 100 plus 150. And negative 110 of 100 is negative 10. Negative 10 plus 150 is 140. And 140 times 100 is $14,000. So the revenue from selling 100 units is $14,000. Now we can generalize this and write the revenue function as a function of x. So what is the revenue function as a function of x? It is, we take the number of units that we sold and we multiply by the price of each unit, which can be expressed as P of x. So this is the formula for the revenue as a function of x. Now we can replace P of x with the actual expression that defined the function. And as a result, what we get is a quadratic function Now, if we read the question in part C, which asks what quantity x maximizes the revenue, and we try to understand this question in the context of this quadratic function, what are they asking us? Every quadratic function has a graph, which is a parabola that is either upright or upside down, depending on the leading coefficient. In this case, the leading coefficient is negative, so our function is opening down. And as an upside down parabola, this function has a maximum. So if we understand what the graph of this function looks like, then we interpret the question in part C as the question about finding the vertex of this parabola. So it asks for which value of x the revenue is maximized. So they're asking us for which value we get the highest point on the parabola, and what is that highest value on the parabola. So basically we just need to figure out the vertex of this parabola. And to find the vertex of the parabola, I'm just going to use the relation that says the x-coordinate of the vertex is equal to negative b over 2a, and the y-coordinate of the vertex is equal to f of negative b over 2a. And in our case, what is a and b? A is negative 1 over 10, and b is 150. So to find the x-coordinate, we just plug everything into this formula. So x is equal to negative 150 divided by 2 times negative 110. So it's 750. And y is f of, well, in this case, it's not going to be f, it's going to be r. It's r of 750. What is r of 750? We use the definition of r to find r of 750. So it's going to be negative 1/10 7 50 times squared plus 150 times 750. So we have to compute this. So I'm just going to factor out 750. And we have negative 75 plus 150, it's 75. So basically here we have 75 times 75 which is $56,250. So to answer the question, what quantity X maximizes the revenue is 750. So to maximize the revenue, we must sell 750. And what is the maximum revenue? The maximum revenue is $56,250. And finally, to answer the question in part D, what price should the company charge to maximize the revenue? We basically need to figure out the price to sell 750 units, which is simply the value of the function p at 750. So the value of the function p at 750 is negative 110 times 750 plus 150, which is 75. So the answer is the price to charge is $75 per item. So this is how we use the properties of quadratic function to solve an applied math problem.